Good morning, good afternoon. Yes, it's a pleasure to speak here. Thanks for the invitation. So this is joint work with Ichia Chen. Let me first recall some results, and then I will tell you what was our goal and what results we obtained. In the 50s of the last century, Łoś and Tarski, independently of each other, proved the following preservation theorem: preservation under induced substructures. Let phi be a first-order sentence, then the class of models of phi is closed under induced substructures, or phi is preserved under induced substructures. That means that if the structure A is a model of phi and B is an induced substructure, then also B is a model of phi. So this is the case if and only if phi is equivalent to a universal sentence. Of course, all of you know that the universal sentence is built up from quantifier-free formulas by means of conjunction, disjunction, and universal quantifier. The non-trivial direction of the Łoś-Tarski theorem is the direction from left to right, and often I will only address this direction. In general, in classical model theory, preservation theorems were proved by an application, more or less explicitly, of the compactness theorem. Then we have no idea whether we can bound the length, in our case, of at least one equivalent universal sentence in terms of the length of phi. Of course, by the completeness theorem, we know there is an algorithm that assigns to every phi closed under induced substructures a universal sentence. However, in the context of algorithms and complexity, questions about how efficiently we can get such a normal form, here an equivalent universal sentence, are of importance. I present an example to see the problem is not trivial. So here we have vocabularies in my talk are finite sets of relation symbols. Here we have the vocabulary tau e consisting of a binary relation symbol e. There we can axiomatize the class of graphs by requiring that E is irreflexive and symmetric. The class of models of this formula here is the class of graph, and the class of finite models is the class of finite graphs. Now let K be greater or equal than 1. Then the class of models of this formula we are going to see in a second is the class of graphs with a vertex cover of size at most k, where this formula says that we have a graph and that there are k selected vertices, x1 up to xk, such that each edge has one end among the selected vertices. It is a very easy exercise to see that the class of models of this formula is closed under induced substructures. But it is by far not so easy to show the existence of a universal sentence equivalent to this formula. This is an exercise for you if you want. So when designing an algorithm making use of an equivalent universal sentence, can I be sure that the length of this universal sentence can be bounded in terms of k? So is it linear in k or polynomial in k? Or in the general case of the Łoś-Tarski theorem, linear or polynomial in the length of the original phi? The answer is no. There is the following result due to Gurevich and shown in 84. If we have any computable function, then there is a first-order sentence such that the class of models of phi is closed under induced substructures, so phi is preserved under induced substructures, but every universal sentence equivalent to phi, logical equivalent to phi, has a length which is bigger than f of the length of phi. In other words, there is no computable bound that serves for all phi whose class of models is closed under induced substructures. Further results of this type are contained in a paper of Davar, Grohe, Kreutzer, and Schweikart of 2007. They showed that model theory makes formulas large. Now, if one is interested in algorithmic problems and complexity questions, one mainly considers classes of finite structures. But does the Łoś-Tarski theorem survive in the finite? So again, let's see an example to better understand the question. So I have here the formula which says that less is a linear order, and there is a minimal element x, and there is a maximal element z. So it is easy to see that it's not closed under induced substructures, the class of models. Of course, take the ordering of the ordinal omega plus 1, then this is, of course, a model of phi. It has a smallest element, the minimal element, and maximal element, namely the ordinal omega. Now look at the induced substructure where you delete the ordinal omega, then we have just the natural numbers, and there is no maximal element. Okay, but the class of finite models of phi is closed under induced substructures. Of course, all finite linear orders have a minimal element and a maximal element. But in the finite, this class of models can be axiomatized by the sentence, less is a linear order, and this is a universal sentence. Hence, if we consider the Łoś-Tarski theorem and we restrict to the finite models, we have a weaker hypothesis, namely only that the class of finite models is closed under induced substructures, but also a weaker conclusion. The phi is equivalent to the universal sentence only in the finite. And we say, or as we say, it is finitely equivalent to the sentence, less is a linear order. This example could suggest that the analog of the Łoś-Tarski theorem holds in finite models. However, already in 1959, Tate answered a corresponding question of Dana Scott negatively. He showed that there is a first-order sentence phi, such that the phi is preserved under induced substructures in the finite, but phi is not finitely equivalent to a universal sentence. So here we pass from the universe of all structures to the universe of finite structures, and we lost the validity of the Łoś-Tarski theorem. If we further restrict the class of structures, then the situation can change again. For example, Atzerias, Davar, and Grohe showed that if k is greater or equal than 1, then the Łoś-Tarski theorem holds for the class of finite structures of 3 with at most k. I don't get into details here because we do not need the notion of 3 with in my talk. It just was an example here. So in 1984, Yuri Gurevich initiated research in an area nowadays known as finite model theory. In particular, the status of all preservation theorems in the finite was analyzed. Essentially, all finite analogues of classical preservation theorems fail. However, for a long time, it was open whether the so-called homomorphism preservation theorem holds. Finally, in 2008, Rossmann showed that it prevails. First order sentence is preserved under homomorphisms in the finite if and only if it is finitely equivalent to an existential positive sentence. Rossmann also could improve the classical homomorphism theorem, the classical homomorphism preservation theorem. He showed a first-order sentence is preserved under homomorphisms on all structures if and only if it is equivalent to an existential positive sentence. This was the classical preservation theorem, but he showed of equal quantifier rank. So with respect to the quantifier rank, or yes, this preservation theorem doesn't make formulas large. While Rossmann obtained the result of 2008 by model theoretic or structural tools, he got the result from 2070 by using tools from circuit complexity. In fact, the title of his talk, the title of his paper was an improved homomorphism preservation theorem from lower bounds in circuit complexity. So let us summarize what we have seen so far. In classical model theory, the preservation theorems were proven in the 50s and 60s of the last century. My impression, they do not play any important role nowadays. And the failure of most preservation theorems in the finite is known for around 40 years. So where does our interest in the Łoś-Tarski theorem comes from? The reason for this, the relationship between universal sentences and forbidden induced substructures, a very special feature of the Łoś-Tarski theorem. Let us see this relationship. First, some notation. If we have a vocabulary, recall that in my talk, vocabularies are finite sets of relation symbols. We denote by structure tau the class of tau structures, and by structure fin tau the class of finite tau structures. If we consider here the vocabulary tau e with a binary relation symbol e, we use the notation for tau e structures used in graph theory, even if they are not graph. We denote the universe by V of G, vertices of G, and E of G is the interpretation of the relation symbol E. Okay, now if we speak of a class of structures, we assume that it is closed under isomorphism. And C will always denote a class of structures. Now, for a set, this is important here, F of tau structures, we denote by forbidden F the class of tau structures that do not contain an induced substructure isomorphic to a structure in F. Briefly, the class of structures with forbidden F, forbidden as induced substructures up to isomorphism. And with forbidden F, fin F, we denote the corresponding class of finite structures with forbidden F. Forbidden, I put here dots, if I always put dots, if this holds for the universe of all structures, or for the universe of finite structure, holds for all structures, for only finite structure. It's closed under isomorphism and induced substructure. This is easy to show. Conversely, if we have a class closed under isomorphism by definition of class and closed under induced substructures, then we can write C as the class of structures with forbidden of all, and we have here all structures which are not in C. One has to think a moment, but one easily sees, due to the closure and induced substructure, that this is correct. I put this F here in quotation marks because this is not a set, this is a class. With A and not in C, every isomorphic structure is not in C. Now, for the class of finite structures in C, we can repair this. It suffices to take at least one structure of every isomorphism type present in this class. So we do this by taking only structures whose universe is an initial segment of natural numbers. So we take all A not in C, whose universe is K in quotation marks, means that in this means that the natural numbers 1 up to K. So we see that for every class of finite structure, the numeral set of forbidden structures suffices. So the question is, when does a finite set F suffice? The following result is at least implicit already in a paper of Ward from 1945. And it is very easy to show. Just analyze a little bit what we can say with universal sentence. So a class of structures is the class of models of a universal sentence if and only if it is the class of structures with a finite F of finite structures. So we have a further algebraic characterization of classes axiomatizable by a universal sentence. And in contrast to the Łoś-Tarski theorem, this result holds in the universe of all structures and in the universe of finite structures. Well, to better understand this, let us see an example. We know that the class of graphs can be axiomatized by a universal sentence. So we have to find an F such that this is forbidden F. Now, the axiom of graphs says that the relation E has to be reflexive and symmetric. And as H0 and H1, we take the least reflexive structure, E structure, and at H1, the least antisymmetric or non-symmetric structure. So as H0, we have a universe just consisting of the natural number 1 and an H or interpretation of E just consists of the pair 1, 1. So this is, of course, reflexive. If this is forbidden, one can easily see that the structure, that the interpretation of E has to be irreflexive. And the same with symmetry. We take the minimal non-symmetric one. We just take as vertices 1 and 2, and as interpretation of E, just the tuple 1, 2. Of course, as we don't have the tuple 2, 1, this is not symmetric. Okay, so here again, Watt's theorem. Forbidden, sometimes also called excluded substructures of one or the other type, play an important role since a long time, mainly in graph theory. For example, already in 1930, Kuratowski showed that the class of finite planar graphs is the class of structures with forbidden topological subsets, the clique of 5 elements and the B clique of size 3 or of size 6, but every part has 3 vertices. I don't get into details here, just to see that there are important results with excluded or forbidden substructures. As the class of finite planar graphs is not axiomatizable in first-order logic, in particular not by a universal sentence, Watt's theorem says us that there is no finite f, such the class of planar finite graphs is the class of structures with forbidden f. A second result of this type, if we have a class of finite graphs which is distinct from the class of all graphs, then if C is minor closed, again, I do not get into details, then C can be characterized by finitely many excluded minors, excluded or forbidden minors. A very important consequence is that every minor closed class of finite graphs is decidable in polynomial time. So let's come back now to Tate's theorem. Tate's theorem tells us that there is a first-order sentence preserved under induced substructures in the finite, but not finitely equivalent to a universal sentence. This means the Łoś-Tarski theorem doesn't hold in the finite. But in the finite, the Łoś-Tarski theorem holds for pi2 sentence. The pi2 sentence is a sentence starting with a bunch of universal quantifiers, then a bunch of existential quantifiers, and something quantifier free. If phi is preserved under induced substructures in the finite, then phi is indeed finitely equivalent to your universal sentence. In 1997, Alechina and Gurevich showed that as phi in Tate's theorem, the theorem above, we can choose a counter example to the Łoś-Tarski theorem of quantifier rank sigma 2, also of which is in sigma 2. So this is the best possible quantifier rank to in view of Compton's theorem. And also they considered or they have a counterexample in the vocabulary tau e. So only a binary relation symbol. However, the class of models of phi is not a class of graphs. So the following problem was still open. Does the Łoś-Tarski theorem hold for finite graphs? Or equivalently, and the terminology important for graph theory, for people in graph theory, is every first-order axiomatizable class of finite graphs closed under induced subgraphs, the class of graphs with a forbidden finite f. Well, we know that every axiomatizable class of structures is first-order interpretable in an axiomatizable class of graphs. This is used frequently in model theory or mathematical logic to transfer results for the class of all structures to graphs. For example, the understandability of first-order logic implies the understandability of the theory of graphs. And also Trachtenbrot's theorem transfers to graphs. The set of a first-order sentence valid in all finite graphs is not recursively enumerable. So why doesn't this work to show the failure of the Łoś-Tarski theorem for finite graphs? The reason: classical interpretations of structures in graphs do not preserve induced substructures. So how did we proceed? First, we analyzed the proofs of Tate's theorem. We realized that it suffices that the interpretation preserves a notion of substructure weaker than the notion of induced substructure, we define the notion of strongly existential interpretation, a class of interpretation that has the property, this preserving property. And finally, a lot of care was needed to construct the strongly existential interpretation that yielded our results. So let us see the results we obtained. We showed Tate's theorem for graphs. There is a class of finite graphs, first order axiomatizable by a sigma tau e sentence and closed under induced subgraphs, but not axiomatizable by a universal sentence. We know that this that pi2 sentence is not possible by Compton's theorem. So this is the best possible result with respect to the quantifier prefix. We also get the analog of Gurevich's theorem. We show that if we have a function which is computable, there is a first order sentence phi such that the class of finite graphs which are models of phi is closed under induced substructures and axiomatizable by a universal sentence. But for every such universal sentence, we have that the length of mu is greater than the length of f of phi. And we showed a lot of understandabilities results. In particular, we showed that there is no algorithm that for any first order sentence, phi, which is equivalent to some universal mu on finite graphs, computes such a mu. Of course, in the three results, you can replace the formulation with universal sentence by the formulation in terms of graphs with forbidden finite f. Okay, thank you very much.
Thank you so much, Jörg. I think that I can speak for everyone when I say that that was a very, very instructive talk. So are there any questions, comments?